So we were to find the dimensions of a rectangle that has a perimeter of 32 inches and a maximum area. So what'd you do? Ideas, thoughts? Squares are rectangles, I like that. Okay, why did you want to focus on a square? All right, so if it has to be a rectangle of some sort, we divide it by 4 to figure out what the possible lengths and widths could be. And 8 would be 8 and 8. So then you found out that with an 8 by 8 rectangle or square, we get an area of 64, right? So let's try some other possibilities. What if it was 1 and 1? That takes up 2 of our 32. What would be left for each of the others? 15 and 15, right? 32 minus 2 is 30. 15 and 15. Are we going to get anywhere near the area that we would have gotten with a square? Absolutely not, right? So your square is going to maximize your area. So what limits do is they help you come up with equations and figure out where we can have maximums or minimums and so forth of curves that aren't necessarily easy to extrapolate individually. Okay, so next slide then talks about the definition of a limit. So a limit, as f of x becomes arbitrarily close to a unique number L, as x approaches c from either side, the limit of f of x as x approaches L is written as this. Okay, so it looks kind of crazy. Lim stands for limit as x approaches c of a function is L. Okay, so that's how we read it. The limit as x approaches c of this function is L. Okay, so we want to be able to estimate some limits. The limit as x approaches 3 of 5x minus 3. So we've got a table here. What do you think we're going to do with that table today? Plug in the numbers. We're going to put 2.9 in for x. Okay? So they're saying, hey, if you decide to try something that's really close to 3, even closer to 3, even closer than that to 3, from the left side, and from the right side, things that are bigger than 3, but pretty close, even closer, you should get a pretty accurate representation. Okay? Now, this is going to seem silly because when we take 5 times 3, we get minus 3 is 12. So this number we could immediately find without doing all this extra work. However, there are times when the function is not defined at that particular value, and therefore we have to come really, really close to that particular number. Thank you. So let's plug them in. 5 times 2.9 minus 3. What do we get? Don't have it? 11.5. 2.99 times 5 minus 3. 2.999 times 5 minus 3. And when we did 3.0001 times 5 minus 3. And 3.01 times 5 minus 3. And 3.1 times 5 minus 3. So do you see that we're on the left side, as the numbers are smaller, getting larger, as far as x is concerned, we're getting closer and closer and closer to 12, right? From the right side, as we're approaching and zeroing in on x equals 3, we're getting closer and closer and closer to 12. Make sense? The limit exists and it is 12, and this was a number that we could have simply plugged in. Does that make sense? We wouldn't have had to do the big table. All right, so next question. Okay, and this makes sense, right? Closer and closer and closer to get to x being 3. Here's our value of x equals 3. The closer and closer and closer we get to y being 12. Okay. All right, so now we want to say, what will the limit as x approaches 0 of x over the quantity, the square root of x plus 9 minus 3 be? So now we say, okay, here's where this limit helps. If we plugged in 0, 0 plus 9 is, what's the square root of 9? And 3 minus 3 is 0. So we would have 0 over 0, which is undefined, right? So we can never divide by 0. So this is why we can't just straight up put that number in. And this is why we need limits. Make sense? All right, so you're going to plug some numbers into the calculator. Okay? Now, is there a way that we can work smarter in our calculator? I wonder. Obviously, we can use our previous entry to help us out. Okay? So we're thinking that we're going to plug in x over, so negative 0.001 divided by, and then in parentheses we're going to do a square root of negative 0.01 plus 9 minus 3. Okay, so I started with my number in the numerator, divided by, open parentheses, this is all being divided, square root, this is what's in the parentheses, and then close that parentheses to close the square root, close this parentheses to close the denominator. Okay, so we press this and say enter, and we get 0.5998. So far so good? Everybody get that? Or did I type something in wrong? Oh, I didn't start with the 2 zeros in front. I started with the 2 zeros in front and I changed it up. My apologies. So when you mess up, you can go and entry and you can go back in and fix. So I should have done a 1 0 in the front and delete one of them. Okay. So 5.998. Everybody good? Is that what you got? Okay, now we can do the same thing and say, so this was 5.998. Now re-enter. At this time I want to have a 0.00, so you have an insert button, right? The shift of delete is insert, so we can insert a 0 in there. And then we can insert a 0 in the other spot. Okay, does everyone see where we're at? And now we press enter. And now we get 5.9998. Okay. Doing it again. Entry, insert a 0. Insert a 0. And we get something that messed up because I hit another button. .00. 5.9998 You see what we're approaching? 6. So this is probably 6 point something something something, right? Let's verify. So 0.0001. So this time we're doing the same thing, but we're getting rid of the negative. Six point 0.000016, right? 4 zeros. So what is the limit as x approaches 0 of that function? 6. Make sense? Okay. By the same token in your calculator, you can go to y equals and you can say I want x over and put that formula in here, right? And then you can go to a table setup and you can tell it where you want your table to start and how to increment. And so you could actually get a table of values. It won't necessarily come up with these nice numbers, but you could have it calculated that way too. Okay, the table function of your calculator. Okay, and there may be a limit function. I don't remember for sure off the top of my head. I can look it up. Okay, so we see that it was undefined at this particular point, but from the left it's approaching 6, from the right it's approaching 6, so we say that that limit exists and the limit is 6. Make sense? Okay. Function doesn't exist at that point, but the limit does. Okay, so here comes another one. What happens if we plug 2 in? Undefined, the denominator's undefined. The denominator's undefined. Okay. So, what's the number that you want to try? And what's another number you want to try? Seems reasonable, right? Okay. So let's try them. Anybody try them already and have those numbers plugged in? All right, so 1.999 to the third, not the sixth. I hit the third. I need to reorient my spot board. Minus 2 times 1.99 to the second plus 2. Wow, this is really off. Times 1.999 minus 4. And then we hit enter. What'd you get? Anybody get something close to 6? Okay, 5.996. Okay, now we're going to try it with 2.001. So second entry, and instead of 1.99, we're going to put it in 2.001. All right, if I type that in right, everybody get something close to 6? So what do you think the limit is as you approach it? 2 from the left and to the right. 6. 6.004. Make sense? Okay. All right, so here's our piecewise function that we saw back in chapter 1. And we want to graph it and figure out what the limit of f of x is as x approaches 5. So f of x equals 1 is a portion of our equation. F of x equals 1. What is f of x actually? What can we replace that with? Y. So if y equals 1, what kind of line are we going to have? Horizontal, right? So y equals 1 everywhere except provided x is not equal to 5. Okay, so y is 1. Y is 1. But it can't be 5, right? At 5, what's y? A negative 2. So we've got a closed circle here. We've got an open circle here. And that's what our graph looks like. So as x approaches 5 from the right, what's our value for y? How high is y? 1. As x approaches 5 from the left, what's our value for y? 1. So even though at that particular point y is negative 2, the limit as x approaches 5 of that function, our answer is going to be 1. From the left it's 1, from the right it's 1, so we call it 1. For this particular function itself, at x equals 5, its value is negative 2, but the limit is 1. Make sense? Okay. All right, so when do limits not exist? Okay, so the limit as f of x as x goes to c does not exist when 3 things happen. Either as x approaches, f of x approaches a different number from the right of c than it does from the left, or if f of x increases or decreases without bound, in other words, you're hitting an asymptote, right? Or if it's oscillating between 2 fixed values as it approaches c. Okay, so we'll see some examples of that. Okay, so let's see that this limit does not exist. As x approaches 0 of x over the absolute value of x. Okay, so let's plug some numbers in. What are good numbers to try? Negative 2, negative 1, 0, 1, 2 are kind of our old standbys, right? So what happens if we put in a negative 2 over the absolute value of negative 2? It'll be a negative 1 because this is still negative 2, but the absolute value of a negative 2 means how far is it from the number line? It's 2 away. And so when we divide that, we get a negative 1. Okay. What about negative 1? What will we get? Negative 1. 0 is undefined. That's why we're trying to use the limit to find this value. What happens when we plug in 1? 1, right? And what happens when we plug in 2? 1. Okay? So when we're at -2, we're at -1. When we were at -1, we're at -1. And at -3, we'd be at -1. And at -4, we'd be at -1 if we filled our table out more fully, right? So it looks like this until it gets to 0, right? Can't be that. We're not defined at 0. But then what happens on the right-hand side? At 1, we're at 1, aren't we? At 2, we're at 2. At 3, or 2, we're at 1. At 3, we're at 1. At 4, we're at 1. So from the right, it's a +1. From the left, it's a -1. So does this limit exist? No, because they're approaching different numbers from both the left and the right. Make sense? Okay. Here's another example. Does the limit of 1 over x to the 4th exist when x is approaching 0? So let's check. What are some good numbers to try? -2, -1, 0, 1, and 2, right? So this one is, of course, not going to exist because we can't divide by 0. So if we take 1 over -2 to the 4th, we're going to get 2 times 2 is 4, times 2 is 8, times 2 is 16. So +1 over 16. Okay, what if it's -1? +1, right? Okay, what if it is a +1? And what if it's 2? 1 over +16. Okay, so what's happening here at -2 for x, we're at +1/16. So we're really close to the x-axis. At 1, -1, we're at 1. And at 0, we don't know, but at +1, we're at 1. And at 2, we're at a +1/16. Okay? What would happen if we did a -1/2? Getting closer to 0. What happens when we take -1/2 and we take it to the 4th power? It comes 2 to the 4th, right? So 2 to the 4th is going to be clear up here at a half. We're at way up here at, what, 16? And the same thing would happen when we were at, if we plugged in a +1/2. We'd be clear up at 16. So go here. Okay. So what's happening? Kind of asymptotic, isn't it? Okay. As we approach 0 from the right, we're approaching infinity, right? And 0 from the, sorry, left and right. This time is from the right. Again, we're approaching infinity, right? So we're not converging on one specific number, are we? And so the limit does not exist here. Make sense? Yes, absolutely. 0.5 to the 1 over 0.5 to the 4th. This 1 over 1/2, which is also the same thing as 1 over 0.5 to the 4th. Okay, and you should get 16. So far, so good? Okay, and what's happening here? Asymptotic to the x-axis, asymptotic to the x-axis. Okay, so here's the last example. Okay, what do you think? Is the limit as x goes to infinity of 1 over the sine of 1 over x going to exist? It isn't, is it? Because it's oscillating. Positive, negative, positive, -1, positive, -1, positive, and -1. Make sense? So there's no way that we can say that this is converging on a specific number. Okay? All right. So this is your assignment.